I want to thank Kyle for his presentation because it really highlights the need for being able to measure specific chemicals and compounds in aqueous systems. And although there are many analytical methods out there to measure all the kinds of compounds, contaminants, chemicals that we are concerned about, the roadblock usually is the sampling methodology, getting it to the lab, the advanced analytical methodology, and the lag time it takes to get that data back to the operator or whoever needs it. And so real-time performance based on that data is greatly limited. So if you're doing things in, any kind of dynamic systems where things are changing or you need real-time data, you really are at a disadvantage. So that really is a driver for our work in trying to develop sensors that will provide real-time data, in situ data. And today I'm going to talk about sort of our first step toward this technology using surface-enhanced Raman scattering spectroscopy as a tool for a real-time sensor. And I'm going to focus on some polyatomic anions and organic compounds in water. But it has applications to all areas that utilize water. Next slide, please. So in the oil and gas industry, there is a need for real-time in situ continual monitoring of a variety of compounds, and I've listed them here. I'm not going to go through why each of them is important. You all know that, but clearly, if you want to maximize product or you want to minimize hazards or maximize safety, you need to keep track of these compounds. And two I'm going to focus on later on in this talk are reduced and oxidized sulfur species related to microbial influenced corrosion and detection of polyoxy anions, as well as I'm going to tell you a little bit about perfluorooctanoic acid because we're using this technology for detecting that compound, and I'll tell you why. Even though it's not related to produced water, it's very important to water. Next slide, please. So the technology or the fundamental chemistry that we're using to detect compounds, this variety of compounds, is based on Raman spectroscopy. And Raman spectroscopy is a very powerful tool or a very powerful spectroscopy in that it gives clear fingerprint spectral data for different compounds based on their chemical structure. In fact, you can even identify different phases and whether a compound is polymorphous or it's crystalline, molecular interactions. So it's a very powerful tool. And I'm not going to go into the details of how it works other than to say you have a very intense monochromatic light impinging upon the molecule of interest. And typically most of that light will reflect off of that molecule and you get what is called Rayleigh scattering. Essentially, there is no change in the wavelength of that incident light. However, 1 out of every 10 million molecules will interact with that energy in such a way that it will cause that molecule to vibrate to create a dipole in it. And so that will then cause what we call Raman scattering, where the wavelength that is emitted is greater than the laser wavelength, meaning that there is a shift in the spectral data that we see. And so we can identify molecules based on their Raman scattering. And now, as I mentioned, that Raman scattering is very, very insensitive, which really prohibits it as a tool for any kind of real-time sensing or even environmental sensors. And that's where we're tackling it with the surface-enhanced Raman spectroscopy. Next slide, please. So just to give you an idea of what Raman spectroscopy can do with respect to environmental samples and what we're thinking about, I show 2 examples here. For example, on the left-hand side, there's a list of tin chloride, alkyl tin chloride compounds. These organotins are often used to prevent barnacles on ship hulls and stuff. So they're a big problem in harbors and such. And what you see here in these spectra are the Raman spectra that relate to each of those different molecules. So the idea is that if we have a mixture of these 4 organotins, and if perfluorooctanoic sulfonate was even in there, we would be able to take a Raman spectrum of that mixture and undergo deconvolution processes to identify which one of those compounds were present and how many of each one of those compounds were present. Over on the right-hand side, I show an example of plastic microparticles that have been collected in ocean water and that have been identified with Raman spectroscopy. And Raman spectroscopy is becoming the tool of choice to identify microplastics in all kinds of water for the very reason that these polymers are so sensitive to Raman. And so you can really identify what kind of polymers we have. No other spectroscopic technique can do this as Raman can for polymers. Next slide, please. So we mentioned that the problem is that we have this incredibly low sensitivity technique. 1 out of every 10 million molecules will experience a Raman scattering. And so, as I said, that prohibits Raman spectroscopy from really being a viable, robust sensor tool. And Raman's been known since 1928, and really it's been confined to the laboratory as a technique. But in the past 20 years, the process of surface-enhanced Raman scattering started to be identified and has become an incredible component to Raman spectroscopy to enhance Raman spectroscopy sensitivity 10 to the 14 to 15 orders of magnitude. So much so that we can detect single molecules or single cells with this process. So how does this work? Well, if you see on the left-hand side, I have a setup there where I have a laser going on and impinging upon these yellow glucose molecules. And in a typical Raman experiment, they would do their Raman scattering, and you can see the Raman scattering waves going to the detector. But in SERS, those glucose molecules are on a surface-modified substrate. And that surface-modified substrate is the key. And that surface-modified substrate has metal nanoparticles on it. And what happens is when that laser impinges upon those metal nanoparticles, the electron cloud in that particle starts oscillating in such a way it creates this plasmonic field and creates these hot spots where if the analyte molecule of interest is in that hot spot, then that Raman process is enhanced many, many orders of magnitude. So the key here is that one wants to get your analyte molecule into that hot spot of that nanoparticle. And that's the challenge, because you can't just mix your analyte and nanoparticles together and look at them. You have to make sure that the analyte molecule gets close enough to that hot spot region. So that is the challenge for what we are working on. Next slide. So right now, our first step toward building continuous real-time sensors is we are working on a sensor test strip. And the idea is that you can see here at the top, we have a blue test strip. And in the middle, we have this thing that kind of looks like a barcode. We call it the photonic sensing chip. That will be the region that has the nanophotonic materials in it. And we'll be able to dip this sensor or this test strip into an aqueous solution. We have to the left of that barcode region, we have a microfiltration paper slip that will filter out any particles or whatever. So we're only looking at dissolved materials. The water with the analyte interacts with that photonic sensing chip. The analytes interact with the photonic nanoparticles, and then you can see here in diagram C, we'll take that test strip and interact it and have it interact with a handheld Ramen spectrometer. There are lots of Ramen spectrometers out there that are commercially available for handheld use. And so the idea is that our test strips will interface with that, so that then the output will be such that it will tell you how much of whatever it is you're looking for. But the key here again is identifying, creating, and getting the chemistry right for those metallic nanoparticles that are going to be in that photonic sensing chip, and making sure that they are specific for the analyte of interest, and they will interact with that analyte of interest, bringing that analyte into that hot spot region. Okay, next step. Next slide, please. So one of the first things one has to do is ensure that nanophotonic sensor chip area has a uniform response. I tell my students, this is like trying to count cows in a pasture. You go out to a cow pasture, the cows are not uniformly spread over the pasture. They're clumped up in regions. So if you were just to take, 5 random measurements, you might come away thinking there are absolutely no cows in this pasture. Or if you hit a clump of cows, you might way overestimate how many cows you have there. So we need to make sure our nanoparticles are evenly spread and our analytes are evenly spread over that surface. So when we take multiple measurements of that nanophotonic chip region, we are getting similar values, and then we can take the average of that, find the standard deviation, etc. And so one of our first steps toward that was this image A is one of our 2-dimensional photonic structures. And we were testing it with R6G dye, which is a very kind of a common dye standard used in Ramen spectroscopy. And you can see here in B, the Ramen spectrum, and you see that there are 6 peaks. And then down in the colored regions, we've shown that all those peaks are evenly spread throughout that surface. So that is the first technical criterion that one has to achieve when you're working with this, and it's much easier said than done. So with that said, we now wanted to turn to some applications in the field, and the first area we started to work with is microbial influence corrosion. Next slide, please. And why corrosion? Well, I and my colleagues have a lot of experience with microbial influence corrosion, and corrosion in the oil and gas industry is a very, very expensive problem. As you can see here, it's estimated that $8.4 billion a year are spent just on corrosion maintenance and repair in the oil and gas industry. And 20 to 30% of that corrosion is estimated to be caused by microbial influence processes. Now, that's probably at the low end. Research shows that it could be as high as 70%. Now, the problem is trying to monitor microbial influence corrosion in a infrastructure, pipelines or whatever, is really, really tough. There's a variety of ways here I list, but they all have their limitations. Either they take a long time, or they're very tedious, or they're very involved. Or you have the issue of, are you measuring planktonic microbes, or are you measuring microbes that are a biofilm on the inside of the pipeline? So it's really a tough process. And so our thinking is, instead of trying to tackle the microbes, let's instead look at the changes in the reduced and oxidized sulfur species that are in this process. And if we can monitor those in real time, we may be able to get a good understanding of if microbial influence corrosion is occurring or not. Next slide, please. So this cartoon just points out that this is the schematic for if you have metal at the bottom and you have sulfate reducing and sulfur oxidizing bacteria. It just shows the entire process of MIC and sulfur cycling when you have this occurring in the oil and gas. And the yellow table on the left-hand side shows the different sulfur species that are present. And so we want to be able to use our sensors to tackle measuring these in real time so we can follow dynamic changes. Next slide, please. And this is feasible because this spectrum of sulfate and its different protonated states, and as well as bisulfide and hydrogen sulfide, they all have their unique fingerprints in Ramen. So this is we feel this is a very feasible task to tackle. But the challenges, as I mentioned earlier, people have used SERS to look at individual molecules on a substrate. But in many cases, that substrate and that molecule are in a very pristine environment of the laboratory. Interactions are optimized. Instead, what we're looking at now are polyanions that are polyanions that are very soluble and can be in a very complex mixture of water. So we have to pay really careful attention to the type of substrate that we are working with. And that's what I'm going to talk about in my next slide. So we built, or we followed a synthetic step from the literature. There's been a lot of work with gold nanostars, and they're really cool little structures here. They're about 50 nanometers from tip to tip. And we wanted to work with gold nanostars rather than, say, a gold sphere, because photonics shows that at the point of those tips, you get really intense photonic hotspots. So we thought this is great because we want nanoparticles that are going to have really big hotspots for our anions to interact with. So that's one challenge. The next challenge is that most metal nanoparticles, whether gold or silver, they have a negative charge on their surface. So if you think about, we're trying to get a negative anion to interact with a negatively charged nanoparticle, it's not going to happen. So we coated these gold nanostars with an alkyl thiol. Sulfur molecules in a thiol, or atoms in a thiol, really bond well with a gold surface. They form a nice covalent bond. And at the end of that alkyl chain, we had a cationic functional group. So now what we have, you can see over here on the left side, I've got my yellow gold nanostar surrounded by an orange circle representing the cationic thiol with a surface of positive charges. And we've demonstrated this using surface charge measurements. We can see the gold nanostar with negative surface, add the thiol, we get a cationic surface. Then we mix that positively charged nanoparticle with our anions of interest, and they electrostatic interact, and now we can get surface enhanced Ramen scattering. Next slide, please. So it's not as good as we want right at this moment. There's a lot of tweaking we need to do. For example, how long the alkyl thiol and the size and all of that of the nanostar. But we are seeing a positive indication that we are getting surface enhanced resonance scattering with our sulfate signal. So sulfate has a very distinct signal at 993 reciprocal centimeters. And what you can see here is that when we have sulfur in the presence of our cationic nanostars, we get a higher peak. Now, this is just one measurement on that surface. We take multiple measurements, again, because it's the cow pasture problem. And we're still trying to get our analytes and nanoparticles evenly distributed. But this box and whisker diagram shows that the blue box shows that sulfate by itself, it has average or median peak area about 2,000 or 20,000, while when we have the sulfate with the cationically charged silver nanoparticles, that signal just about a little bit more than doubles. So we're on the right track. We just have to fine tune several aspects of this. We also, next slide, please. We also are interested in nitrate and nitrite using, again, the silver nanoparticles with the cation exchange materials. And nitrate is not, we're not getting as much SERS as we'd hope, but there is a little bit there. However, with nitrite, what's really exciting is that nitrite by itself, we don't see anything, but in the presence of the silver nanoparticles, we see two peaks indicative of nitrite. So nitrite is really dependent on that SERS. So we've also worked with phosphate. Phosphate is a tough one to deal with respect to Ramen, because it doesn't give a very strong Ramen signal as it is. So we have not had much luck yet with Ramen. We also want to try perchlorates, and just because perchlorates are an important issue in many areas with respect to groundwater contamination. So that's one example of our work with polyoxy anions. The next area, next slide, please. The next area we've been working with, it doesn't directly deal with produced water, but it is a big problem with water resources across the United States, actually around the world. And that is the contamination by perfluoroalkyl substances, PFAS. And perfluoroalkyl substances, we use literally hundreds of these fluorinated organic compounds for a variety of purposes. Any kind of non-stick water repellent spray you use on your boots or your carpet, it's made out of these perfluorinated organic compounds. Their biggest use is with firefighting foams, particularly in aviation areas, because they can withstand high heat. They will smother the flames. If you have an aviation spill, a fuel spill, and it's on fire, last thing you want to do is spray water on it, because the fuel will float to the top and the water will carry it away while it's all on fire. So you just make the mess bigger trying to treat an aviation fuel fire with water. The PFOA and PFAS, they're great. They form this foam, they smother the fire, but they are forever chemicals, and they do have toxicological effects on humans. And so when you look at groundwater, surface water around a lot of military bases that have aviation, or civilian Air Force bases, or industries that utilize these compounds, you will often find contamination. Even in leachate coming from landfills has these compounds in it, because they are leaching out of consumer products, carpets, clothing or apparel that we've had these materials on. And to analyze them, it's really a challenge. First of all, we're talking about very low concentrations, nanograms per liter. And literally sometimes we're talking about, just a few molecules per liter of sample. And I often tease my students, I say, you got to be careful, because if you get, your cat rolls around on the carpet in the morning before you go to work, and you pet your cat or you pick it up, you could come to the lab and contaminate the sample. So when one is going out in the environment and collecting these samples, you have to be very careful. You have to make sure you do not contaminate them. Also, the analytical processes behind this are really challenging. because these molecules are surfactant in nature. So there is a big need for a rapid test that will be able to identify these compounds in place, in situ, in real time. Next slide, please. And I just put this map up here because this is from the Environmental Working Group, showing where perfluoroalkyl substances have been detected in drinking water. And the blue dots are municipal sources. The purple dots, I believe, are near industrial complexes, and the purple are military bases, and the red are near industrial complexes. The point of this slide is that PFAS supposedly contaminates up to at least a third of all drinking water resources that we know of. It's probably greater. And next slide, please.
Mark, I just want to do a quick time check. Just have a few minutes left.
Okay, I'm sorry. So I'll tell you what, I'll skip this slide. So anyway, we're working with this, and we're focusing in on the carbon-fluorine bond. Carbon halogen bonds appear between 600 to 800. Because they are unique in the environment, we can target that region specifically for looking at those. And here we've been able to actually detect PFOA at 0.4 nanograms per liter. Now this is a big thing, because this is much below where many states and the EPA are going to be targeting regulation levels. So we're still working on developing these strips into something that is robust enough to take out into the field or to use, but we can get down to that. And I also want to mention that, our next step is going to be with carbon chlorine type bonds, organic solvents that contain chlorine. So next slide, please. So kind of wrapping it up, our goal is to envision having this technology could be used for a variety of things. Eventually, if enough sampling is done, and if this could be automated, one could do real-time modeling of chemical transport and fate, and eventually coupling this with artificial intelligence or machine learning, getting into what-if scenarios and prediction capabilities for evaluating treatment and remediation methods, whether it's remediating groundwater or remediating microbial influenced corrosion, it doesn't matter. So next slide, the last slide. So I just want to acknowledge my colleagues. We're a group very diverse. There's me, an environmental chemist, Dr. Wang, electrical engineer, Dr. Mohagalu, petroleum, Joseph Lita, petroleum and environmental microbiology, and Dan Schuert, who works with us trying to help us keep these projects funded. So if you have any questions, I would love to talk to you. If you have any ideas about types of analytes you're concerned about, I'd love to talk with you and see what we could maybe help you with. So with that, I'll
All right, we've got time for about one question, and I'm not seeing any questions in the chat. Sorry, Jason, I missed your chats earlier. Any questions for Mark?
This is David Levitt, Mark, and
yes.
I have one quick question. Was really interested in the widespread contamination of the fluorinated compounds. Are they endocrine disruptors? Have you found anything in the literature about that?
I don't think, don't quote me on this. I don't think they're endocrine disruptors. They're more, it's carcinogenic issues that targeting certain organ systems. And they're hydrophobic. So they, the problem is they can, for example, like accumulate in mother's milk. So infant that's breastfeeding gets a heavy dose. But I don't know if they're endocrine disruptors, but don't quote me on that.
Would you know whether or not they're fairly volatile, or are they non-volatile compounds?
Well, they're pretty non-volatile because of the carboxylic acid group or the sulfate groups. When we're talking about PFOA and PFAS, they have typically they have a permanent negative charge because they're deprotonated at circumneutral pHs. So they have a pretty low vapor pressure.
All right, thank you.
Oh, I see someone in the chat said, yeah, they are endocrine disrupting.
Oh,
Yeah.